In Chapter 4, we're going to focus on the Pythagoras Theorem. Now, this is a theorem that allows us to solve for the missing sides of any right triangle. Now, recall, a right triangle is a triangle that has one angle that is exactly 90 degrees. Right opposite the right angle is what we call the hypotenuse. The hypotenuse of any right triangle is always the longest side of the triangle. Now, the sides that make the right angle are called the legs. So the two sides of the triangle that make the right angle, we call the legs. So Pythagoras' theorem is simply the leg squared times the other leg squared is equal to hypotenuse squared. We often see this written as a shorthand, a squared plus b squared equals c squared. For the rest of this video, we're going to look at how we can use Pythagoras' theorem to help us solve for the missing sides of various right triangles. So let's look at our first example. Okay, in example 1, we're asked to find the length of the missing side. So first you need to identify if that side is a hypotenuse or a leg so that you can plug it into the Pythagoras theorem. So we plug in our two legs, 5 squared plus 12 squared equals x squared. Then we just simply solve using our algebraic form. Now, usually when we take the square root of 169, I get plus or minus the square root of 13. But notice in this case, I don't write the plus or minus. Now, the reason for this is that we're looking at a length of a side of an object, a physical object in space. And we know that distance is always positive. We can't have something that's a negative square root of 13 length. So that's the reason why we would write our answer as simply the square root of 13. Also, remember at this time, if you can simplify the radicals, always simplify your radicals and always write your answer in exact form. In this case, we cannot simplify it down. Example 2, the missing side happens to be a leg because it's the side that forms the right angle. So we would set this up with x squared plus 5 squared equals 11 squared. Using our algebra, simplifying this problem down until we get x squared is equal to 96. Then we take the square root of 96. Notice I only use the positive because we're looking at distance of this object. And so then I need to figure out how 96 breaks down. 96 is the same as 16 plus 6, which means that it is x is equal to 4, the square root of 6 yards. Remember to put your units of measurements if units of measurements are given in the problem. Starting with example 3, we're going to look at some more complex applications of the Pythagoras theorem. So in this example, notice that I have two unknowns, x and y, and I have multiple triangles, but I only have this one right angle here. So how you figure this out is you look at one right triangle that has one missing side. So in this case, I want to look at this red triangle, and x is a leg, so I have x squared plus 2 squared equals 6 squared. Using algebra to solve for x, we figure out that for this triangle, x is equal to the square root of 32, but the square root of 32 breaks down to 16 times 2, which is the square root of 4, which is 4 times the square root of 2. If we look at the very large right triangle, that includes the missing side y, so it'd be this large green triangle. Now notice that it has to have a right angle, so we had to include the right angle, and we have one side that's missing. Now we're going to use the Pythagorean theorem to solve for this green right triangle. We notice that y in this case is a leg, so we're going to set this up as 4 the square root of 2 squared plus y squared equals 15 squared. Using our rules of exponential functions and algebra, we will simplify this down until we find that y is equal to the square root of 193. The square root of 193 does not break down, so this is the answer to this problem. In this next example, we have a right trapezoid in which we're trying to solve for the missing side x. To do this, we need to realize that the trapezoid here is consistent of a rectangle and a right triangle. So using our knowledge of rectangles and right triangles, we can figure out that this new right triangle that actually involves the side x that I'm highlighting in red. To figure out the solution to this problem, I only need to look at this small right triangle of 4 centimeters by 2 centimeters with the x, or the hypotenuse, is the missing side. So I use our Pythagoras Theorem, simplifying it down and solving for the x. I figured out that an x must be equal to 2 the square root of 5 centimeters. For example C, I have two right triangles here. So I'm going to look at this first red right triangle. Now the reason I chose to work with this one first is it only has one missing side, which is the hypotenuse of x. So I'm going to use the Pythagorean theorem to solve for the hypotenuse x in this red right triangle. Simplifying it down, we end up with that x is equal to 13. Now that I know x is 13, if I look at this other right triangle, I only have one missing side now, which is the y. So this green right triangle, we have y squared plus 13 squared equals 20 squared, since the missing side is a leg this time. Solving for y squared, we easily figure out that y is equal to the square root of 231. Now I'm not sure if 231 breaks down or not, so I try it and I see I don't have any perfect squares. So y is equal to the square root of 231. First glance example D looks very intimidating and confusing, but if I break this down to individual parts and solve for the missing sides of right triangles, this is actually pretty easy to solve. So I'm going to start with this green right triangle, and I'm going to label the missing leg as y. So I'm going to use my Pythagoras theorem to solve for y in this triangle. Since y is a leg, I'd set it up as y squared plus 2 squared equals 5 squared, the hypotenuse. Applying my algebra knowledge and simplifying this down, I will end up with y is equal to the square root of 21. Now that I know the missing side y, I'm going to look at this red rectangle that's to the left of the green right triangle I just solved for, and I'm going to identify the lengths of each of the sides of this rectangle. So it's given that the bottom is 10, and I just figured out y is the square root of 21. So I know that parallel sides of rectangles are congruent, so I can find that when I convert this information to the blue right triangle that's above the rectangle, I know this bottom leg must be 10, since it's the length of the red rectangle. And since this entire length of this side is x, and I figured out this one little part of this side is the square root of 21, that means for this leg of the blue right triangle, it must be x minus the square root of 21 length. In our Pythagorean theorem, we have a first leg of x minus the square root of 21, quantity squared, plus a second leg of 10 squared, equal to our hypotenuse of 18 squared. Now remember, when we have x minus square root of 21 quantity squared, we have to use the full method, multiplying this by each other. Don't distribute the square. So using full, I end up with x squared minus 2 the square root of 21x plus 21, and then I still have that 10 squared, which is 10 squared, which is 100, and that 324, which is 18 squared. Combining like terms and simplifying down. And remember, anytime I have a quadratic, in order to solve a quadratic, I gotta get it equal to 0, so I'm going to subtract 324 from each side. And then I can solve this any method I want. I'm going to use the quadratic formula to solve this, since I have that b term of 2 the square root of 21, which is kind of hard to work with. So remember, our quadratic formula is opposite of b plus or minus square root of b squared minus 4ac all over 2a. So identify your a, your b, and your c. Plug that into our quadratic formula. Use our knowledge of algebra to simplify this problem down. Now I know the square root of 896 can also be broken down. I can rewrite that as 64 times 14. 64 is a perfect square, so that's 2 to the square root of 21 plus or minus 8, the square root of 14 over 2. Now I can take out my GCF of 2 from the top and cancel it with the 2 from the bottom. Next I look at, I have a plus or minus here, but remember, I cannot have a negative length when I'm dealing with a distance, a length of a physical object. So I need to figure out which of these will give me a negative answer and then eliminate it. So it's very obvious that I can see, since I started with a positive value, that subtracting the 4, the square root of 14, will give me the negative. So therefore, the length of x is the square root of 21 plus 4, the square root of 14. And you solved your last problem.